Hello and welcome to Week 8, Lecture 1 of CO 442642 Graph Theory. Today we'll be discussing the graph minor structure theorem. Before we do that, I thought we'll need one additional ingredient, which is like tree decompositions, but they're called path decompositions. So let me explain that first. So a path decomposition of a graph G is a tree decomposition TV, where T is a path. So you're doing this decomposition, but only in a path-like way instead of tree-like way. So path decompositions are a bit easier to work with than tree decompositions. And in a similar way as to tree width, we can define the path width of a graph G, denoted PW of G, as the minimum width of a path decomposition of G. So where width again is the maximum size of the bags, but minus the 1, again, for the reasons that trees want to have tree width 1, or here paths want to have path width 1. So that's path width. So we won't really dive into this or prove the things about it. I thought I would just state the obvious analogs and theorems that were proved before. So one is a theorem of Robertson and Seymour that says a graph has large path width if and only if it contains a large complete binary tree as a minor. So remember the grid theorem, where we proved that a graph is, well, we didn't prove that, but we said that a graph has large tree width if it only contains a grid as a minor. And so again, where there are functions for large and large there. But here it turns out what things don't have nice path decompositions, or low width path decompositions, they're binary trees, kind of the complete binary trees. They're too tree-like to admit low width path decompositions. So that's one analog. It's not that hard to prove. It's easier than the grid theorem, but we won't go through that. And as a corollary, just as we had for tree decompositions, we learned that if you exclude a planar graph, is if and only if you get bounded tree width. Here, H minor free graphs have bounded path width if and only if H is a forest, right? Because if we forbid a forest, then that every forest would embed in some complete binary tree. And so their theorem would imply bounded path width. And if you aren't forbidding a forest, then really you're allowing all the complete binary trees. Okay? Because then they'd have a cycle, so you'd have all the binary trees, and you'd have large path width. So that's an easy corollary of their theorem. So analogs of the grid theorem, analogs of the planar structure theorem. So if you wanted to know what happens when you forbid a graph as a forest, not only do you get bounded tree width, but you get this additional bounded path width as additional structure. So that's quite nice. All right, and then the other point about path decompositions I wanted to make is there's an analog of cops and robbers there, which I alluded to, which is you have the K cops, and again they move in helicopters, and you have a robber who's infinitely fast but can't go through cops. Except this time, instead of being visible to the cops, the robber is invisible to the cops. And a different way to think about this is equivalently, you're kind of cleaning a graph of a plague, which infects along the edges. And so you need to kind of have the cops sweep the graph from left to right to make sure that you've ridded the graph of the plague. And so in that sense, it becomes clear that a monotonic winning cop strategy is equivalent to a path decomposition of width k minus 1. That you're not allowed to branch according to where the robber goes because you can no longer see the robber. And actually, Laplague and Kourousis and Papadimitriou independently had shown that k cops have a monotonic winning strategy if and only if they have a winning strategy. So we won't get into what would be a robber winning strategy here, or the analog of brambles, etc. But this began to inspire the Seymour and Thomas work, which did it when the robber was visible and led to brambles there. So that's all I wanted to say about path decompositions. So you can learn and study more about them. They're, again, nice, kind of easier versions of tree decompositions. But they will be importantly come up in this statement of the graph minor structure theorem. So I thought I'd say a little bit more about them. So what is the graph minor structure theorem? Well, again, we're studying minors these weeks, and the main idea is it gives you a theorem that tells you what happens, what's the structure of graphs when you exclude a complete graph as a minor. So to do that, I'm going to need a definition, though. So let G be a graph and TV be a tree decomposition of G. For T1, T2, an edge, then the adhesion set for T1 and T2 is simply the intersection of the two bags. VT1 intersect VT2. And the adhesion of the decomposition is the maximum size of its adhesion sets. So when we had kind of low width tree decompositions, we had this idea then of kind of low adhesion, but here we're formalizing that a bit. And then we talked a little bit about torsos, but I'm going to be a little bit more formal here. So for T, a vertex in the tree decomposition, we define the torso of the decomposition at that node T as the graph obtained from the bag by also adding the complete subgraphs of its adhesion sets to the other vertices around it in the tree. So essentially, if you view it from this point, you would understand that a graph, if you have a tree decomposition of a graph, what you're really doing is you're taking the k-sums of the torsos of the decomposition over their adhesion sets. So that's where k-sums factors into tree decomposition theory. And now, given this understanding, I can state the graph minor structure theorem, proved by Robertson and Seymour in the series of papers on graph minor. So the proof of this eventually appeared in 2003. And it says that for every t at least 5, there exists this k, such that every graph with no kt minor has a tree decomposition whose torsos are k nearly embeddable in a surface in which kt does not embed. So what is that saying? Well, of course, what's the structure of graphs when you have no kt minor? Well, you could embed on, if t is 5, you'd have all planar graphs. More generally, you could have all graphs on surfaces where it doesn't embed, or too low a genus. And really, as we discussed before, there's really not much better of a structure for those kinds of graphs. But beyond that, it's still possible, a la Wagner's theorem and other constructions, that you could take these graphs and kind of take small k-sums of them, and so glue them. So that's kind of why part of that's necessary, that you need to be able to have this k-sums or tree decomposition idea. You need surfaces, but you also need two additional things we're going to talk about, which is what this k nearly embeddable will be. So I haven't yet defined k nearly embeddable. That'll be on the next slide, so let's proceed to do that. So what does it mean to be k nearly embeddable? We say a graph G is k nearly embeddable on a surface sigma if it can be embedded in sigma except for two things. Apices, so we're going to allow apex vertices, so that's just additional vertices. So i.e. we're allowed to delete some bounded number of vertices and try to get an embedding. And then something weird called vortices, which we're allowed a bounded number of vortices. So we're going to be except for at most k apices and except for at most k vortices. So what are this picture maybe look like? So apices will just kind of be vertices up in heaven. Again, we'll delete them. We don't care how they attach to the rest of the graph. They can attach to everything. So that'll be fine. And then we have these strange things called vortices. So what's a vortex? It's a disk in the surface that's cut out from the surface, such that some of the vertices, v1 to vm of G, are on the boundary of the disk, and attached is a graph H with a path decomposition, that's TV there, of width at most k, where, so here's where path decompositions are coming in, but they're going to respect somehow the embedding of the disk. So how is that going to work? Well, then T will be, of course, a path, T1 up to Tm, but we're going to have that Vi is in VTI for all I and M. So somehow the bags, as they go around the cycle, that you have to make sure that they contain the vertex, each bag should contain the vertex on it. So it kind of creates a linear ordering, a path decomposition that kind of interacts with the surface in a linear way. So here's some kind of rough picture of that. So again, we have V1 up to Vm, you've cut that disk out, and so you have the rest of the graph, is embedded in the surface, but then I'm allowed to add more edges, this additional graph H with a path decomposition inside. So in principle, it's somewhat like you're only allowed to go to vertices that are close to you in the cycle. That's not quite true, because you could have a vertex that just appears, say, in all the bags. But in principle, that's kind of what it's saying, that as you move around, you're allowed, your k cops in the path decomposition, and those could be repeated, but eventually they're not, and they cycle through as you do in the surface. So that's a vortex, and so you're allowed a bounded number of apices and vortices. So is there a converse is a good question. Does the converse of the graph minor structure theorem hold? Is it an if and only if? So if I have this structure, is it clear that I don't contain a KT minor? So maybe think about that. The answer is kind of not necessarily. Of course, the numbers weren't quite right, but, qualitatively it's going to be true. So it's not precise enough. It's not an if and only if, but what is true is that every graph that has a tree decomposition whose torsos are k-nearly embeddable on a surface in which kt does not embed does not contain k of t as a minor for some function f of t. So it's some qualitative converse, some if and only if. In the same way as the grid theorem is kind of like an approximate if and only if. Okay, so that's what I wanted to say about the graph minor structure theorem. We'll come back to it, but now let me kind of maybe talk about some additional results to mop up this graph minor theory. So one is the disjoint paths problem, and this is related to minor testing. And it goes like this. Fix an integer k and let s1, sk, t1, tk be vertices in a graph G. When do there exist k internally vertex disjoint paths from the si's to the ti's? So when can you get paths? But again, here not Menger's, but actually ordered. So for Menger's, we know it would just be cut. Here it's, I want s1 to go to t1, I want s2 to go to t2, etc. And so when k is 1, of course, this is trivial, just asking if there is a path. With 2, there's a nice answer. It's called the two-paths theorem, proved by Seymour. And it says that there does not exist two disjoint paths from S1 to T1 and S2 to T2 if and only if G can be obtained from a planar graph H with S1, S2, T1, T2 on the outer face of H in that order via three sums with other graphs. So here's a picture. So if you think about it, if you have a planar graph and you had them in this kind of wrong order, you can't get both the S1, T1 and the S2, T2 path. They'd have to cross planar-wise. So it's impossible. Beyond that, you can also actually take triangles in the graph and just kind of plug any graph on a three-sum with that triangle. You can kind of stick it in there. And they won't be helpful to creating the paths because, if you could have done it with this, then just remove it. You're only going to use two of the vertices of the triangle. And so those three sums would not be helpful to making the graph. So that's essentially the theorem. But so that's one direction kind of showing why it would be necessary, but actually it's sufficient that this is not the case. So that's a nice theorem. We'll again go through that proof. It gets a bit tricky, but that can answer the kind of the two paths question. Now it's still not clear, could you even, test this property? Maybe you could think of the three sums, maybe you could then test planarity and realize maybe then you could believe that when k is 2, it's doable. But actually they proved that for every fixed k, deciding the disjoint paths problem can be done in polynomial time. So you're going to do it, in v of g to some power that depends on the k. And here's a very rough proof idea. So today we're just going to do a couple very rough proof ideas of some of these minor theorems that are very hard. So here's one way to do it, is you consider two cases. So does your graph have bounded tree width or not? So if your graph had bounded tree width, the idea is you could just use dynamic programming that we alluded to kind of iteratively figure out whether or not you can build up these paths. Whereas if the graph does not have bounded tree width, then by the grid theorem, there'd have to contain a large grid minor. And if you contain a large grid minor, much larger than in the sense of k, maybe it's something like 2 to the k or something, you begin to realize that you could delete an irrelevant edge in the center of the grid. So, I'm skipping some details there. How does the rest of the graph connect to the minor, etc.? But roughly that would be the concept, would be that, I would maybe that there'd be some edge in the center of the grid that is not actually useful to creating the paths. So somehow it's clear that, if I could get the paths with the edge, then I could reroute and get the paths without it. And so I'd prove it's irrelevant, and so I will just delete it and kind of go by induction and say, okay, now I reduce to a smaller graph, etc. So it's some very rough idea, maybe didn't cover all the cases, but you can see how tree width and grid minors can play an important conceptual role in deciding this kind of question, which seems to be nothing about grids or minors or tree width, but it's fundamental. Now, as a corollary, maybe you can understand that for every fixed graph H, you get that deciding if graph G contains H as a minor can be done in polynomial time. So this is probably more clear to you that it works for subdivisions, which is true there, that you can, think of testing every single vertex, and I want paths, so I want maybe subdivisions then. So that would be that. But what about for minors? Well, you can just kind of think of all the possible ways that a minor could be found as a subdivision, and then to test all of those. And there's only finitely many. So that's the idea behind why the disjoint paths is connected to minor testing. And now I want to finish up going back to well-quasi-ordering. So we're going to go back to well-quasi-ordering one more time and talk about the graph minor theorem and sketch a proof of that in our time remaining. And then we'll move on from minor. We'll talk a little bit more about other things with minors, but really this will be it for the graph minor theory. So let's do that. So recall the following consequence of the grid theorem, which I alluded to at the beginning when we talked about kind of the path analog, is that if H is planar, then the class of H minor free graphs has bounded tree width. So, and this is a really if and only if, that only if and only if H is planar, but let's just use the if H is planar. So what does that mean? Well, if you recall Kruskal's theorem, trees are well quasi-ordered, and actually we alluded that Robertson and Seymour proved that bounded tree width graphs are well quasi-ordered. So what does that mean? We get that the class of H minor free graphs is well quasi-ordered, and should of course say that if H is planar there. So this would mean if H is planar, we've really done the well quasi-ordering just from the grid theorem, and now we want to kind of do it in general. So let me, before I do the graph minor theorem proof sketch in general, let me just say a little bit about surfaces. So one consequence, if you remember, of the graph minor theorem, that there isn't an infinite anti-chain of minors, was that the set of forbidden minors for the class of graphs embeddable in a surface sigma is finite, right? That's a special minor closed class. So how would you prove this? Well, you don't need the full power of the graph minor structure theorem for this. Instead, here would be some kind of proof sketch. So let H0, H1 be the forbidden minors for this class. Case 1, and again we're going to use cases, and we're going to use kind of grids as the idea. Case 1 would be that H0 does not contain a large grid as a minor. If it doesn't contain a large grid as a minor, then we'll get that the H0 minor free graphs will be well quasi-ordered, and hence there's a good pair in H1, H2, etc. Case 2 would be that H0 contains a large grid as a minor. So the case 1 there would be more that infinitely many don't, so you'd have bounded tree width, and then you'd have infinitely many that would have bounded tree width, and so then you get a good pair, is what it really should say. Case 2, you contain a large grid as a minor, and then the key is you'd again take this idea of where the grid, you take an edge in the center of the grid, you delete it, now you embed in sigma, but then so does H0 if you re-embed the grid part. So I won't go through that. You can check DSTL for kind of a sketch of this proof using facts about topology and how large grids would have to embed in a surface. But again, you kind of see the dichotomy by seeing whether or not you contain a large grid as a minor. So now back to the graph minor theorem. So the same ideas show up if you want to sketch a proof of the graph minor theorem. And again, this would be quite long to do in detail and relies on the graph minor structure theorem, which takes many papers to prove. But here's roughly what you would do. So you'd assume naught, so you'd have a bad sequence, this infinite anti-chain, so let's call it G0, G1, etc. The case 1 would be that G0 is planar, and if you exclude planar graphs, then the rest, of course, does not contain that planar graph, so the rest of G1, etc. would have to have bounded tree width, so they'd be well quasi-ordered, so you won't have a bad sequence. So there'd be a good pair in G1, G2, that's a contradiction. Case 2 is that G0 is not planar, right? So then if you're kind of not planar, what does it mean? Well, then it means that by the graph minor structure theorem, G0 minor free graphs have a tree decomposition whose torsos are K nearly embeddable, in which KT does not embed. So recall that. So then what do we do from there? So we have this kind of structure theorem. So here we're using the structure theorem. Well, the point is that there would exist an infinite subsequence that all embed in the same surface. There are only finitely many, and then we just really have to go by induction on the genus. So note though that there's these apices and these vortices, and we'll skip that, but the idea is if they're bounded, then in the same way that Kruskal's kind of works, and you could do bounded tree width, then those are just additional add-ons. So we won't go through that, but adding a bounded number of apices is again only an additional factor in the wellquasiorder, and they're finite and they're bounded. And the same idea with the vortices. So really what it suffices is then to try to argue that you're wellquasiordered kind of for this nearly embeddable or more really embeddable for the surface sigma. And if sigma is the sphere, if you're S0, then it would mean that H0 is planar. And again, if you excluded a planar graph, then all the rest of them would have bounded tree width. You'd get a good pair contradiction. So you could assume that you're not actually the sphere. And then you can just kind of go by induction on the genus. Why? Because as we learned last week, if you excluded H0, then it would bound the edge width of H1, H2. Because every graph there would live inside of, as a minor of some large hexagonal grid. And so if we kind of exclude that, then it would mean that only kind of low edge width graphs would be possible. And so then if they all have low edge width, they all have bounded non-contractible cycles. You can cut along these to reduce the structure of H1 and H2 to new graphs. And then there's two cases. If infinitely many of them have cycles that are non-separating, then the idea is when you cut along them, you get each one transforms into a graph on a smaller genus, which would have a good pair by induction, except you have to worry about the cycles, but you can view those as a bounded set of apex vertices. So if we're also doing it with apices, then we'd be fine. The other case is that the cycles are kind of separating, and then you get the pairs then what would happen is each graph H1, H2 would separate into two smaller graphs that are kind of glued, and then either you're kind of getting these smaller genus graphs, and there'd be, if you did it with rooted kind of roots there, then you'd actually again find a good pair in each one. Kind of if the smaller ones are wellquasiordered, then pairs of them are, and so we'd be able to again find a good pair, a contradiction. So that's some very rough sketch of the graph minor structure theorem proof at a very high level. Again, read Diestel goes through this in a little bit more detail than we have time for now. But that should give you, these three sketches should give you some sense of this dichotomy. What's going on. We're always kind of doing cases. Do you have a large grid minor or not? Then excluding you gets bounded tree width or not. If we exclude planar graphs, indeed we do get bounded tree width. Using those, or we get grids. If we get large grids, maybe we can delete the edge in the center of the grid. So those all combine together. And maybe also the bigger takeaway, besides those kind of proof techniques with grids and tree width, is this very nice graph minor structure theorem. That really the structure of excluding the graph as a minor is surfaces and tree compositions plus these apex vertices and vortices that were allowed, but really that's about it. And so it really tells you, if aliens only learned about minors and came up with kind of graph minor theory, that they'd still find surfaces because they're somehow a fundamental concept. This topological graph theory that we studied is fundamental to this graph minor structure theory, but so is the tree decompositions and the tree width side, these K-sums. So they're all kind of fundamentally going into the structure of excluding graphs as a minor. So that's what we've kind of reviewed, from the graph minor structure theorem to the grid theorem to the graph minor theorem, all very nice in this graph minor theory. So until next time, see you then.